Chapter 19, Lesson 2. In this lesson we've been talking, on the first lesson we've been talking quite a bit about entropy. And we're going to transition, we're going to talk some more about entropy, but now in a more quantitative way. So we said that entropy changes can be looked at for different systems, whether chemical or physical systems. And here's a graph of how entropy changes as a function of temperature for any substance. So we're increasing the temperature this way, and we're checking what happens to entropy. In general, as you increase the temperature, the entropy goes up. The molecules become more disordered, because remember, entropy is a measure of the disorder of a system, and nature loves to make more disorder. And disorder is a driving force of chemical reactions and of nature in general. So you'll see for any given substance there's a linear increase in disorder when you increase the temperature as you're going through say for a solid. The higher the temperature, the more motion the molecules have, so the solids becomes more and more disordered. Now anytime you're in a phase change like melting, notice how quickly the entropy shoots up. There's a sudden increase in entropy, and that's because the molecules that were ordered in fixed positions are no longer, remember for a solid they're essentially fixed in relation to each other, but for a liquid there is freedom of motion now. So there's a big increase in entropy. And if you keep heating a liquid, it goes up linearly because the molecules can now speed up faster and faster. But then there's a huge jump anytime you go from a liquid to a gas. Very big jump in the boiling phase change. And this makes sense because now the particles are completely free of one another. They can go anywhere they want. So this is by far the biggest increase in entropy for a substance, is going from a liquid to a gas. And then finally, as you keep heating a gas, the gas speeds up and increases in entropy. Now you'll see that the slope here for the gas is greater than the slope for the solid. So, and actually greater than the slope for a liquid too. So gas also has a steeper slope because the more you heat it up, the faster it decreases in order or increases in disorder. That's another feature of this graph. So this again is more of a qualitative look at entropy. Let's now take a look at a quantitative view of entropy. And before we do that, we're going to summarize. First, we're going to give you a third law of thermodynamics, which again relates to entropy. And both the second and the third law of thermodynamics are related to entropy. And the third law says that the entropy of a pure crystalline substance at absolute zero is zero. Now, this seems like an unnecessary law, but it is necessary to define, say, the zero conditions. So since there is no heat, there is no disorder. In other words, the only time you can have zero disorder is if you're absolute zero, is if you're at absolute zero. And because getting to absolute zero is practically impossible, even though scientists have gotten pretty close to within a few billionths of a degree Kelvin, really any system at a higher temperature is full of disorder. So at room temperature, all the substances that we have around us are full of disorder. That's the idea. That's the third law of thermodynamics. It's more of a technicality, if you would. So we've given you the first, the second, and the third law of thermodynamics. Let's now summarize those three. And there's a way of phrasing this in the modern way. So remember, the first law says you cannot create or destroy energy or matter, which means you can't win. The second law says that you're constantly increasing in disorder. So you're always losing order. You're always losing something for the whole system, for the whole process. So you can't break even. And the third law says that you're only at zero entropy if you're at absolute zero, which is impossible to get to. So you can't even get out of the game. You can't win, you can't break even, you can't get out of the game. So think about your options at this point. Okay, now let's take a look at the quantitative aspect of entropy. So these are called standard entropies, and standard because they've been defined under standard conditions. So if you take a look, all these gases, this first section, gases have the most entropy, the highest amount of entropy. And if you analyze the gases themselves, the more atoms you have in the gas, the higher the entropy in general. So if you just have N2, you got 191. But if you have CH3OH gas, you have a higher number for entropy. By the way, we should mention that entropy, the units of entropy, are a bit strange. It's joules per mole Kelvin. So it is related to energy, because remember, joules, this idea of joules is a measure of energy. So entropy is measuring, you can say, a form of energy, if you would. Then for the liquids have less entropy than do solids in general, even though if you have a liquid that's has a lot of atoms, it may end up having less entropy than, say, a gas that has just two hydrogens, the simplest possible. And then for solids have the least amount of entropy. So, but the same rule applies. You can, the more atoms you have in the solid, the higher would be its entropy. So these entropy values are have been determined for many, many substances. In fact, they are all in Appendix C. And we will introduce you to the entropy values in Appendix C. So the general term here, or the general idea here is with increasing molecular mass or molar mass, entropy increases. So here's a theoretical view of it. Larger and more complex molecules have greater entropies. And the reason for this is because larger molecules have more possibility for motion. So something like propane having 3 carbons, you can move the carbon, you can, for example, spin these carbons around the central carbon, but in ethane, you can only spin it once. In methane, you can't spin them at all. So there's more possibility for motion, more motion possible. And that's why the more atoms you have on a molecule, the greater the entropy. You can see that the entropy is greatest for propane with 3 carbons versus ethane with 2 carbons versus methane with just 1. Now, we can calculate entropy changes just like we calculated enthalpy changes. If you recall, to get the change for the enthalpy of the reaction, say, delta, remember, is final minus initial, and if we apply this to chemical reactions, this is in general final minus initial, and if we apply it to chemical reactions, this becomes products minus reactants. So here's the equation, and the equation looks complex again, but it says that the change in the entropy for the reaction, for the chemical reaction, is the summation, this is sigma, sum of all the products minus the sum of all the reactants. And then N here and M mean you have to multiply by how many moles you have, and that makes sense because the more moles you have, the higher the entropy is going to be, so you have to consider that. And by the way, this little knot, this little 0, this little mark, means under standard conditions. You'll see this, you've actually seen it in delta H, and you'll see it here in delta S as well. So we'll be able to do a few of these examples. So here's an example. We want to calculate the change in entropy for the synthesis of ammonia, this reaction here. And this is going to be as easy as looking up the entropies of these 3 substances and plugging them into the equation of products minus reactants. So open up to Appendix C in your book. Let's look up nitrogen. And make sure you take a look at diatomic nitrogen. You have to make sure you match up not only the formula, but also gaseous diatomic nitrogen. And that should give us 191.50. And by the way, this will be joules. Entropy is given in joules, in contrast to enthalpy, which is given in kilojoules. So 191.5. Look up hydrogen. 130.58 joules. And finally, ammonia should be under nitrogen, its principal element. 192.5 joules. joules. Now, all of these entropy values, notice, are positive, and this is true. Anything above absolute zero has an amount of entropy. That's from the third law of thermodynamics. If you're at any sort of temperature above zero, absolute zero, you've got an amount of entropy. So now we'll do products minus reactants. So why don't we? So we're going to do products minus reactants. In this case, we're going to do 2 multiplied by 192.5. That's our products. Minus, and let's put this whole thing in brackets. We have nitrogen, which is 191.5, plus 3 hydrogens, which is 130.58. So go ahead and plug this into your calculator, and I recommend doing it step by step. That way we don't miss anything. So why don't we evaluate the first portion here? 2 multiplied by 192.5, or I'm sorry, 191.5. This should be a 1. Try that again. We have 383.00 actually for significant figures. Minus, go ahead and evaluate that portion. Oh, actually this is 192, I'm sorry. That's right, we have, because we're looking at these values. Notice how interesting, it is interesting that the two are very similar. So I apologize there. So let's add another one. So twice that, 385. Here we are, 85. And then evaluating the second part of it should give us roughly 583.24 joules. So combining the two numbers, should give us negative 198.24 joules, and this is our entropy change. Now notice that the entropy change is negative, and recall that if it's negative, this means entropy is decreasing. Disorder is decreasing because our delta S is negative, and that's exactly what's happening. We have 4 moles of gas on the left side and only 2 moles of gas on the right side. So we did increase in order or decreased in disorder. So chemistry wins again. Now I'm going to go through into just a little bit more about entropy. This is not on your notes, I realize, but this is just for your entertainment purposes. Feel free to jot it down. But you will see a few of these designations for entropy. This equation here is very famous to define entropy. Again, entropy is S. And entropy can be defined as, in fact, these are the units of entropy. If you take a look at the units of entropy are, go back to the table, units of entropy are joules per mole Kelvin. So Q is heat, which gives us joules, and temperature will be in Kelvin. That's where you'll have joule per Kelvin for entropy, and usually it's given on a per molar basis. So the numbers we've just seen, entropy has a unit again of joules per mole Kelvin. And this is another equation. If you know the heat content, if you know how much heat the system has, just divide by the temperature at which the system is at. You can also find the change in the same way. You can derive it and just put a delta in front of both of these and find the change in entropy. If you know the change in heat, as long as it happens at a stable temperature, you can find the change in entropy. So these are maybe useful. You'll see these in other classes and textbooks. And here is this is the last slide, but this is the more technical definition of entropy. Entropy was first defined, or the theory for it was given to us by Mr. Ludwig Boltzmann back in the 1800s. And he was the first to describe entropy at the molecular level, and he gave a nice mathematical explanation of it. So molecules can be thought of as having many different states relating to their motion. So you can say if a molecule flips, that's one of its states, and if a molecule is vibrating That's another one of its states. So here are a few possibilities of the same molecule being in all these states. And there are an enormous amount of states possible for any given molecule, and these will be called microstates. And so W is defined as the microstate a molecule is in. So the equation for entropy is K, which is Boltzmann's constant, which is 1.38 e negative 23, multiplied by the natural log of W. Now, if you know anything about this equation, K is a tiny number already, notice, to the 10 to the negative 23rd. And we're taking the ln of another number. Anytime you take the log of a number, remember, you pull out its power. So if W is a big number like 10 to the 24th, ln just becomes 24. So you know that W must be very, very, very large. In other words, there's a lot of microstates. There's a lot of ways of thinking of a molecule. There's many, many ways in which a molecule can exist, and in fact it exists in many of these ways. The more ways, the more entropy you have. So this is the famous equation, the technical equation of entropy. And this will conclude for us lesson 2 of chapter 19.